Patel, visiting professor IMPRI, former professor, Tata Institute of Social Sciences, TIS, Mumbai. Now, without further ado, let us start the program. It is my honor to invite Professor Nilanjan Banik to start the program. Over to you, sir.
Thank you, Tripta. So welcome back to this program. In fact, let me start where we ended in the previous session, which is we were dealing with the multiple regression. Now, for the audience, can you please allow me for the screen sharing, please? For the benefit of the audience, I think let's try to give you some intuitive idea as to what we are doing, and then I will go to the data, and then I'll show you exactly what we are doing and why that part of what we are doing is so important. Okay, so this is basically now when we were student, I found two books very useful, and I thought that as a reference material. Although I have said Basic Econometrics by Damodar Gujarati, there is another book by Introduction to Economics. So that is by James Stock and Mark Watson. So these two books are quite fascinating to read and easy to understand, and I highly recommend to have a look at these two books. Okay, so let's see, what basically we are looking at is as follows. So if you think what we did in the previous class, and as I said that I'm going to carry forward that discussion so that each one of you exactly know what is happening. We were doing a few things. First is we were dealing with the error terms. Now, what are the error? Error is basically we are trying to estimate something. Okay, going by what we did in the previous class, we are trying to estimate the sales price of the house. If you have the data with you, you will find that we are trying to explain the sales price of a house as a function of various other independent variables, namely lot size, number of bedroom, square feet areas, number of bathrooms, and the year the house was built. Okay, so we have sets of independent variable, and we were trying to predict, and I'm going to showcase today how we predict the price of the house when we are dealing with the cross-sectional data. I'm sure that you are also having a session on time series analysis, where you can again use as methodology time series analysis to predict the price of house or predict price of stocks. But here, basically, because we are dealing with classical linear regression function, we are basically trying to predict the outcome variable, which in this case is the sales price of the house, using sets of independent variables, which I have just now mentioned. And when you are predicting, the other thing you should keep in mind, you are trying to minimize the error, minimize the sum of square of error. Now, why square of error? Why not error? I'll explain in a bit. But the idea is error can both be negative as well as positive. And even if you have huge negative error and huge positive error, both of them may cancel each other. Okay, and therefore it is not a good idea just to look into what we call minimum average deviation, or MAD. Okay, so basically you take into account the sum of square of error, and ideally the way the classical linear regression function works, they look into the first two moments condition, namely the mean and the variance. They don't go beyond the first two moment conditions. So basically what I'm trying to say is, if I'm looking into this thing, if I'm looking into let's say the moments condition, you will find that in this case I'm just looking into the mean and the variance. The variance being the second moment condition, mean is the first moment condition, but we don't go beyond variance, which is kurtosis or skewness or fifth or sixth, that is something you have to deal in the methodology called GMM, which is generalized method of moments. Okay, so that is something I'm not going to do today, but maybe in the future, if we are doing some other classes, we can also check into or have a look into that. Okay, now when I'm saying that basically we are trying to minimize the sum of square of error, basically what I'm trying to get at, and these are the pictures I have taken from this book by Gujarati, because that is something I'm sure most of us have access to. So here, if you see what is happening, if I'm looking into U1 vis-a-vis U4, you will find that the magnitude of error which are given by U1 and U4 is much higher than what you see in comparison to U3 and U2. Okay, but if you are just minimizing the sum of the summation of error without taking the sum of square of error, they are giving equal weightage to both U1 and let's say U3, which should not be the case, because the error is actually much higher when I'm considering U1 as opposed to U3. The same story goes with when I'm comparing, let's say, U4 with U2. And therefore, here what ideally one should do is to minimize the sum of square of error, and that is something you see we are doing in the context of classical linear regression function. Okay. Now, the other things, and as I said, that I'm actually going to showcase each one of this. So you see that a few other things I should also mention before I go to the Excel worksheet. And let me open this for the discussion in case you have any question, because that will make this much more interesting in the sense that, for instance, why is it? So basically, what we are trying to say, this is SRF. SRF stands for sample regression function. Okay. This R for regression, and then you have function. Okay. Now I'm going to ask you two questions. Okay, and I'm sure that you have all heard about this. The first thing is they are saying X is non-stochastic, and the other thing which you have heard is something called stratified sample. My question to you is, and anyone can answer to motivate this discussion, this is very interesting as you actually go and start collecting the data. I'm sure that you have heard these two words. One is this X is non-stochastic and stratified sample. Anyone who wants to answer this? And I have requested Dr. Arjun that just to make this class more interesting, you can actually speak rather than writing it on the chat box. Okay. So if anyone
want to speak and participate, please raise your hand, right? So that we can give you.
Yeah.
Yogesh, yeah, right.
So I'm asking two very intuitive but very important questions. I think Yogesh has a question. Yes, Yogesh, please ask.
Sir, X is non-stochastic is like X is fixed over the sample. Like it, like you explained in the last class, it remains fixed over the different samples. It won't vary over the same size.
Okay, that's what I said. I'm not contradicting, but let's try to make it much more relevant in the sense that let's say that y is my height, okay, and x is my age. Okay, so just to ensure that we are on the same page. So let's say that this is my height, okay, and we are saying that x is my age, okay. Now, as Yogesh is saying that x is fixed in repeated sample, and what you see over here is I have one sample regression function, okay. The idea is we want to actually go as close as possible to the actual data. Now, in order to go as close as possible to the actual data, I have to know the population. Population is actually how the data is behaving, okay. Now, let's assume that I have, here you see x1, x2, x3, and x4. And let's say that I want to rename x1 as when your age is 10 years, okay, x2 as when your age is 15 years, x3 as when your age is 17 years, and x4 is when your age is 20 years, okay. So let me repeat, 10, 15, 17, and 20, okay. So when I am saying that x is fixed in repeated sample, there are two things which are happening. I'm not changing this x1 being 10, x2 being 15, x3 being 17, and x4 being 20, okay. So that is fixed whether I'm collecting this data, let's say from Hyderabad, or I'm collecting this data, let's say from Bangalore, or I'm collecting this data, let's say from Calcutta, or I'm collecting this data from, let's say, from Delhi, okay. So let me repeat, x is fixed in repeated sample means I am actually fixing the age, which in this case are 10 years, 15 years, 17 years, and 20 years. Okay, is that clear? Whenever I am going and collecting this data, so let's say this SRF that you see on your screen represent Hyderabad. If I were to draw this for Calcutta, if I were to draw this for Bangalore, if I were to draw this for Delhi, or for that matter, Ahmedabad, or for that matter, any other city in India, this X, which I am fixing, remain fixed as 10 years, 15 years, 17 years, and 20 years. Clear? Now, how does this stratified thing comes into place? Again, what is the objective? The objective is we want to estimate what is the mean height given that your age is, let's say, 10 years, given that your age is 15 years, given that your age is 17 years, given that your age is 20 years. Because after 20, we are assuming that we are not becoming any more taller. And therefore, that height thing we can try to neglect once you have attained your 20 years of age. Are you guys getting it, what I'm trying to say? So the first thing which I've said that X is fixed in repeated sample, this is what I meant, is when I'm actually categorizing the data, irrespective of which sample I'm looking at, be it Delhi, be it Bangalore, be it Calcutta, be it Ahmedabad, Mumbai, wherever we are doing. We are still kind of fixing that age as 10, 15, 17, and 20. My second question, which is related to my first question, is how that stratification is happening here. What does this word stratified sample means? In fact, whenever you are collecting the data, you are always collecting data on the basis of stratified sampling technique. You ask anyone in working with NSSO or Department of Statistics, they are going to tell you that if you're not stratifying the sample, it's going to come out with a biased estimate. Okay. Yes, Yogesh, I think you have a
The stratified sample study is like dividing population into different groups based on either places we could say, like based on Bangalore, on basis on different age groups, or 15 age group for different cities, or 17 age group for different cities. We could certify on the grouping of people basically.
Grouping of people, that's fine, but just to try to tie it up with what we are discussing right now, can you elaborate it a little bit more? So we have this data 10 years, 15 years, 17 years, and 20 years across various cities. Where does this stratification comes into picture?
Stratification comes if we divide population in different cities.
No. You give me the example, like the example I'm trying to give you. Okay, so let's try do this. Let's see. Let me open this. And so stratification basically is trying to tell me the number of the stratification is in a way is telling me the number of observation. Okay, number of observation across each age group. So number of observation across each age group means, just to build on what Yogesh is trying to say, let's say that my population, is saying, let's say from the population, I am saying that the number of people in the age group of 10 years in India is, let's say, 20%. Okay. Number of people in the age group of 15 years is, let's say, 25%. Okay. Number of people in the age group of 17 years is, let's say, 30%. And number of people in the age group of 20 years is, let's say, so 20, 55, 45, 75, 25%. Okay. So now this is you should keep in mind intuitively what is happening is, let's say I have total number of sample in each city that I'm collecting is 1,000 number of observation, okay, in each city. So basically what it's telling, when I'm actually plotting this corresponding to 10 years, I'm actually collecting data on how many people, because I have to follow what is there in the population, right? So I have some answer. Let's see. Given that age is a continuous variable, the stratification may be better in ranges. Yes, Aditi, we are actually doing this here. We are doing the stratification. So the stratification we are doing, we are actually following from the population. The ranges is in terms of the age. Of course, you can, like I have taken only 4 age group. You can actually take more number of age group. That is not going to change the observation or the outcome. Okay. Priti is saying stratification to pick homogeneous sample.
Yeah, what I'm saying is just to take, equal number of participants from each group.
No. That's exactly what I'm not saying, Priti.
Okay.
Basically, what I'm saying is your observation should be because at the end of the day, what we are trying to do is we are trying to reach the population from the sample, right? So your estimate should be as close as to the estimate of what you see in the population, because it's not possible for me to get the population data, and therefore you do the sampling. And in the population, if I'm saying that the number of people who are falling in the age group of 10 years is 20%, number of people who are falling in the age group of 15 years is 25%, 17 years is 35%, 20 years is 25%. Basically, what I'm trying to say is if I'm collecting 1,000, if my sample size is 1,000, so ideally for the 10 years, I should have 20% of 1,000 is 200 as the number of observation. Okay, for 15 years, I should have being able to collect data on 250. Or for 17 years, I should be able to collect data on 300 people. And for 20 years, I should be able to collect data on. So it's not same across. But if you're randomly collecting, which is not following stratified sample, then of course, what you're saying is correct. But ideally, you should follow a stratified sampling procedure. Okay, Priti, does it answer your question? I have another question.
Yes.
Yeah,
Yes, perfectly. Yeah,
probability
proportion to
proportion
sample.
to the no. So the here the probability is proportion to the population, right? The sample
Population, yeah,
probability.
yeah. Sorry, yeah, population.
Any other question? Very good thought. Any other question, guys? Please make it clear, because otherwise you will again get confused. Okay. So this is
You
yeah.
can. Aditi had a question, but she can speak. No issues, sir. Go ahead.
Okay. Anyone can ask any question, okay? Because then only you'll understand. Otherwise, it will be. Okay. So basically, what we are trying to do, therefore, is we are trying to. So here, as I said, that beta. Okay. So now let me ask the other question: why beta is linear? Okay. Because we are saying that beta. Again, what is beta? Because if I'm looking into this y equal to beta 2x plus u, where u is my error, x, now we have dealt with this idea that x is a non-stochastic. It is fixed in repeated sample, and we are drawing x in proportion to what we see in the context of population. That's what stratification stands for. In addition to that, there are two other things that we are trying to argue. Is one is we are saying that the slope of the beta or the betas are linear. My question to you is, why you think beta is linear? Anyone can answer. What is the problem if beta become non-linear? So I'm saying that this slope is linear. Okay, what happens if beta is non-linear? Aditi is saying, let's see what she's saying. We only want to get one value of beta, therefore linear. Yes, in a way, Aditi, because what happens is, let's say I have beta to the power raised to the power cube, then basically what means is for this polynomial, I will have 3 unit root, and therefore beta is not unique, and therefore we want to have a unique beta, and therefore the beta has to be linear. Okay, so that is. On the other hand, x can both be linear as well as non-linear. Okay, now why is that? Because many times, yes, so both Aditi and Yogesh are correct, saying that the value of beta has to be univariate, or we want a unique value for beta. These are also called marginal coefficient. Okay, now why marginal? Because even if you have more than 1x, ideally when we are trying to interpret the beta, we are assuming that other x are constant. Okay, so that's why it's called the marginal coefficient. X, on the other hand, can be non-linear. Think of this, and in fact, most of the cases x is non-linear. The most useful example which I gave is basically if you think your return to your education, okay, it's highly nonlinear because if you're, let's say, if you have done only schooling, you have just passed 10th grade exam, you may be working in various places as in Reliance Smart or Big Buzzer as delivery boys and stuff like that. So your return is quite small because these are highly unskilled type of labor. Now let's say that you have now passed 10 plus 2. As you progress, as you pass, let's say, now you have passed your graduation, you've done your graduation. Of course, you are entitled to write various exams, and if you get qualify for one such exam, your return to income is going to increase. And of course, beyond that, if you are doing a master's, MBA, or PhD, your return is going to increase manifold more. Okay, and therefore X is highly nonlinear when the outcome variable is income, and X, we are saying the number of years that you are spending on education. Okay, so that's what I'm trying to say, that X can be both linear and non-linear, and therefore depending upon what we are dealing with, we'll have to check that. Okay, now there are two other assumptions that we want to make. In fact, three other assumptions. One is the error, it is have equal variance. Okay, we in the next class I'm going to showcase, and these three things that you see: heteroscedasticity, multicollinearity, and autocorrelation. These are the deviation from the classical linear function. Okay, deviation from classical linear regression model, CLRM. CLRM means you are deviating from the classical linear regression model, and in case of heteroscedasticity, the deviation which happens is the error terms, the variance of the error terms are no more uniform. Okay, it changes from various one X to another. Okay, and what is the problem with that? It makes our beta inefficient. You know, it gets a higher variance, and when beta gets a higher variance, then of course our projection or our forecast can go haywire, and therefore ideally you should have a homoscedastic variance. Then the other deviation is autocorrelation, which is basically saying that the error terms in one period is dependent on the error terms on previous, or maybe influencing the error term in the next period. So that is autocorrelation. So if the error terms are related to one another across space, across time, then you have a problem of autocorrelation. Here we are dealing with the cross-sectional data. So basically it's saying that the error terms across sample are related, which should not be the case. Again, I will show you how to detect autocorrelation. And finally, we have this concept of multicollinearity, which is basically saying that, as I said, this marginal coefficient, when we are trying to estimate, you are basically saying that once I am actually trying to see the impact of X1 variable on Y, I am assuming X2 or X3, which are the other explanatory variables, those are constant. Okay, those are, so basically the X, the independent variables that we are considering are independent of one another. But if they are kind of dependent on one another, then we have a problem, and that is called multicollinearity. So that I will also showcase how you can detect multicollinearity in the next class. Okay, so we are actually going with few assumptions. One is the beta is going to be linear, X is non-stochastic. The way we are collecting our data, it has to be stratified. Stratified on the basis of what? Stratified on the basis of what we observe in the population. Why stratification is important? Because we want to, through our sample regression function, estimate a function which is as close or which kind of mimic as closely as what we see in the population. Then we are also saying that the error term are related across space or across cross-section, as well as it is kind of not related across time. And then we are going to end our this lecture series by telling you how to check for whether the data are suffering from heteroscedasticity, autocorrelation, and multi-collinearity. Okay, so that is what we are going to do. And now let's see in the here in the next slide. So let's say that if I'm going, what is happening? This, if I'm going to the next slide, so this is what we were dealing with. So this is what we are dealing with is. So these are the things we have already said, that we are estimating the sample regression function, which we are calling y hat. X variables are non-stochastic. X can be linear or non-linear. And we also said that OLS, in case of ordinary least square, we are assuming all the hypothesis testing that we are going to do is in the form of these are normally distributed, or the density is normal. Okay, if it is not normal, and there is something called Jacques-Bera test statistics, I'm going to showcase that as well. It's called Jacques-Bera statistics. Bera is our statistician. He actually grew up in Calcutta, from Bardhaman district. So this Jacques-Bera, these are two well-known statisticians. They came out with, if you remember in the first class, I said that you'll have to plot the data using this formula norm dist, right? But as we run the regression, you will find that you can use this Jacques-Bera test statistics, try to understand whether y is following a normal distribution, which is quite important, because under the classical linear regression function, we are assuming both the error and the beta. These are following a normal distribution. Okay, these are following a standard normal or normal distribution, and this one stands for univariate, or this is the variance is 1, which is basically saying that it's a homoscedastic. Okay, if at all we find that the betas are not following the normal distribution, we have to go for non-parametric estimation, and there are ways to figure that out as well. And as I said, that in case of OLS, they are looking into only two moments condition, namely mean and variance. They don't go beyond the second moment condition. But if we were to include all other moment condition, this methodology is known as generalized methods of moments. Okay, so GMM, I'm sure you've heard that. Most of the statistical package will come out with this GMM statistical technique. Okay, any question? Okay, so thereafter, what we did is, as you know, that if it rings a bell, that we were talking about in the first class, very first class, we were saying that why we need to know about the distribution function, and the reason being is we want to see or predict the outcome variables, and we actually spoke about this positively skewed distribution function, where we said that it actually helps us to understand that what is the extent of income inequality. Okay, we were discussing that in the context of India, and that's what we were discussing in the very first class. Okay, now moving forward, let's see what else we have. Now let me try to give you some more idea. So we have said about this. By the way, this Jagbera statistics, they actually take the ratio of skewness and kurtosis, okay, and then they try to form an idea that whether this distribution of the density function is normally distributed or not. Okay. Now, just to re-emphasize and rephrase and bring home the point one more time. This again, this I'm taking from your book, from the book that we are following, which is Gujarati. And this is how the stratified sampling is working. You see that here you have family income and consumption expenditure data. So basically you are assuming that how much you consume or how much your consumption expenditure is a function of your income. So here, if you're, let's say that for this group, who are falling in the income bracket of 80, their consumption pattern is you're collecting data on 5 individual. Why 5 individual? Again, you are looking into the population and try to see what is the number of people falling under that particular group. Okay, and in proportion to what you see in the population, you are collecting. So this n why you see that more number of people are there when the income is 100, because maybe from the population you are seeing that there are more number of representatives who are earning more number of income. So here if I ask you just to make sense, what do you think is the maximum number of people, how much they are earning? Given the population, given the stratification, where do you think which income level you have maximum number of people? It is 140. You see, in this group I have more number of observation, 1 2 3 4 5 6 7. Okay, and the way you draw the conditional mean is basically it is E over E. E is the expectation, Y given X. Okay, so why, how I'm getting this 101? Basically, what is the, if I'm assuming that the in terms of probability I'm assigning equal weight to collect my sample, here each one will come with a probability of 1 by 7. Okay, so 7 over 707 is 101. Likewise, 678 over 1 2 3 4 5 6, you will get this number 103. Likewise, 750 over 1 2 3 4 5 6, you get 125. So this is what we call conditional mean, and the sample regression function is nothing but if I'm actually drawing the conditional mean, so that's my sample. That is my sample regression function. That's what you get over here. Clear? So this is in the context of one variable. Now, if we have more than one variable, which is the case in most of the cases, as we see, you will find that in most of the cases, if we have more than one explanatory variable, we are basically trying to fit a hyperplane. It's because it's not possible to draw a two-dimensional figure as you see over here. Basically, there you'll have to fit a hyperplane, and you can imagine each one of the observation as small ping pong balls, which is floating in the air, and your objective is to fit the hyperplane in such a way so that the sum of square of error is minimum. Okay, so that's what is being done in the context of this classical linear regression function. I have another very intuitive question for you guys. What is the difference between correlation and regression? Anyone? Because what we are doing, I could have done the same thing by standardizing both the data and then try to get a correlation between both the data. If I were to see whether there is any relationship between two variables. In fact, correlation is the starting point of regression. My question therefore is, what do you think? What do you think is the difference between correlation and regression? Anyone? So correlation is, Yogesh is saying it should be univariate. So correlation is basically trying to capture the linear relationship, because if you look into the formula of correlation, it's covariance over variance, right? Covariance of X and Y over the variance, right? So it's actually capturing a linear relationship, and it is only capturing the relationship between two variables, right? But on the other hand, when we are doing the regression, it is capturing both linear as well as non-linear relationship, and it is also accommodating more than one variable. So that is the advantage of doing regression analysis, and therefore why you find that this classical linear regression function or the multivariate regression is so popular. Okay. Now coming back to this, this is how the data look like. Okay, so what again, taking from your book, is what you see here is, what you have here is, I have drawn the regression function, but only for two cross section. If I were to draw it for the entire India, okay, so for all the cities I'm collecting the samples, so I will have, let's say, depending upon the number of states, if I am considering, let's say, 21 states, and the capital city from each one of the state, then I will have 21 such sample regression function, and the average of that will give me the population regression function. Okay, so in that way, I can actually go from the sample to the population, and thereafter what you do is, I want to tell you some of the important formula before we actually go for this thing. So the population regression function, you will find, is a little bit different than the sample regression function. Again, why? Because what you observe in the context of India as a whole will differ from what you find in the context of Hyderabad, what you find in the context of Bangalore, Calcutta, Noida, Delhi, so on and so forth. Okay, but even then, you will find that even when you have calculated the sample regression function, the actual Y, okay, is different than your predicted Y. So going by the sample regression function, you are predicting, in this case, the weekly consumption expenditure to be, let's say, Y I hat. But in actual, your value is yi. Okay, so this difference, which is still there in spite of you doing a very smart job in predicting the y, this thing, something which you are not able to capture from your data, is what we call RSS, or the error terms. Okay, so this ui hat that you see, this is also called residual sum of square. The moment I use the word square, basically I am saying ui square. Okay, otherwise error, so if I take the summation of all the error, this is going to be 0, because there will be positive error, there will be negative error. Again, why positive and negative? You will have to go back to this concept of mean. Anything deviation from the mean, you transform the data and you add the error, you will get 0. Okay, so the simplest example which I give in the class to my student is, you don't have to do anything. You just create one variable 1, 2, 3, 4, 5, and then subtract. If I have 1, 2, 3, 4, 5, the mean is 3. I subtract mean from 1 minus 3, 2 minus 3, 3 minus 3, 4 minus 3, 5 minus 3. I get a transformed variable, which is the standardized variable. I add that, you will find it's coming to be 0. That's same concept we are getting over here, because this is a conditional mean, the SRF, yeah. And if I'm adding the error, both positive and negative, it's going to give me a 0. And I'm going to showcase that in a moment from now. Any question, guys? Any question? Any one of you? Please feel free to ask, because we are actually dealing with the basic. Okay. See, the other thing which is quite important, as I said, that we are trying to minimize the sum of square of error. So this is we are trying to minimize it respect to what? As I said, that imagine this as a hyperplane. So I'm choosing the beta. I'm choosing this beta 2. Beta 1 is my intercept. Beta 2 are my slope coefficient. So I'm trying to choose beta so that I'm trying to minimize the sum of square of error. So unfortunately, I cannot do mathematics over here too much, because the idea is to showcase using the data. But if for those of you who are more interested, if I take the let's say differentiation of ui square with respect to delta beta 1, okay, what I get is this 2 will come to the in the front. So basically, if I were to write this in terms of the differentiation with respect to, let's say, beta 1 hat, what I get is, and of course, this will be equal to 0. Why? Because we are trying to minimize this. We are trying to minimize this error. Okay, so the minimize will happen when minimize or maximize, whatever thing, the first order condition is, you always equate it to 0. Now, if I do this, basically what I get is something like this. This 2 will come in the front, and then I have this, the same yi minus beta 1 hat minus beta 2x. This one. And then from this beta, I have again a negative number, right? Because if I differentiate beta 1 hat with beta 1 hat, I get negative number. So essentially what I'm getting is negative 2 summation of yi minus yi hat, okay, equal to 0. Now, why this is? Because this is equal to yi hat, okay. Now, this is nothing but, I can rewrite this equation, summation epsilon equal to 0, which actually means that summation of epsilon is equal to 0. So the summation of the error is going to be 0, exactly what we are predicting in our model, okay. If you have any question, please feel free to ask. But again, I'm going to showcase using the data just a moment from now. Now, here, the other thing you should know is the more the relationship, what is this? This is the deviation from the mean. X is my explanatory variable, Y is my explained variable. So this is basically the covariance. So the higher the covariance or the correlation between X and Y, the more is the value of beta, which makes sense, right? Because what is beta 2? It is basically capturing the slope coefficient. So the higher the relationship, the more is the value of beta 2, okay? On the other hand, if I have a higher variance in X and Y is not changing, that means my beta 2 is going to be insignificant or going to be very small, okay? So these are the intuitive thing that you should keep in mind. The other thing is what I said, that because X and U is what? U is again the error terms. This is my, these are not correlated, okay? So therefore you see that this number is 0 by assumption. What if they are correlated? If they are correlated, then we have a problem of what we call is endogeneity. I'm sure that you have heard about this. So how you take care of the problem of endogeneity? You have to go for the instrument variable. I'm sure you have heard about this, and we can also, that's outside the scope of this class, but we can also do separate session on endogeneity, simultaneous equation, instrumental variable, so on and so forth. Okay. Finally, before going forward, this term, this is the estimate of the error. So the variance of the error, you find it is inversely related. What is n? N is the number of observation. Number of observation. So the higher the number of observation, the more is the denominator and less is the sigma hat square. So which is a good thing. Okay. So error is going to fall if I am able to increase the number of observations. So keep that in mind. Okay. The error of what? The variance of the, this is the estimate of the variance of the error terms. Okay. So the variance of the error term is going to fall the more. So for the context of classical linear regression function, as I said, that they take into account only the two moments conditions. So these are the two moments. I'm not looking into other moments condition. I'm just looking into two moments conditions, the first and the second moment, namely the mean and the variance. So this is basically saying it's homoscedastic. And then this is zero mean. And why zero mean? I have just explained, because you are looking into the conditional mean. And this implies it's no serial correlation or absence of autocorrelation. Okay. So this is the thing we have already dealt. Absence of autocorrelation. Okay. And we are going to use this T statistics. And here again, what is my, in a very simple term, this is my equation. If I have one variable, okay, let's say I have my, in the context of what we were discussing, let's say I have X as my age and Y as my height. So basically we are trying to predict the height in terms of the number of years or how many years you are old. Okay. And here, what is my null hypothesis? The null is always beta is equal to 0, and the alternate is beta is not equal to 0. Okay, so this is what we are going to do. And whether the beta is, so this T statistics is basically going to tell us that whether we should, whether this variable is statistically significant or not. Okay, so if we are finding that beta is the T value is not statistically significant, it implies that X is not influencing my Y. Okay, let me repeat it one more time. If the T statistics of what? T statistics of the beta is not statistically significant, it implies X is not influencing or having any impact on the variability of Y. Okay, so keep that in mind. Any question, guys? Please ask question. So basically, we are going to actually do few things in the context of, because when we are running the regression, when we are trying to predict, in this case, what we are trying to predict, we are trying to predict the sales price. Okay. Now, when you are trying to predict the sales price, why unnecessarily take the pain of including all the x's? Okay, so the x was my square feet, x was my number of bedroom, x was number of bathroom, x was also year built. So you say that there is both time and cost factor collecting data on each one of the x. Okay, I could have done a better job or a more simpler job without collecting data on each one of them. Instead, if someone asks me to predict the value of y, I just go to the mean value. Okay, so that is the other way, mean value of y. Okay, but whether the mean value, whether y hat or y bar, again, what is y bar? Y bar is the average sales price. So if I'm collecting data on 51 observation, so y bar is what is the average price I'm getting. Okay, so whether y bar or y hat, that is something that the F-cast statistics is going to help us understand. Okay, so if F test statistics is statistically significant, what it is basically telling us is it is telling us that Y bar is doing a better or a poorer job. Y hat is doing a better job. So if F test is statistically significant, if it is statistically significant, then what we are suggesting is Y hat is a better predictor than Y bar. So keep that in mind. Also, the other important result of F test is we can actually decide whether to actually include these variables. Okay, include this variable, for instance, bedroom, bathroom, square feet, year built, so on and so forth. Okay, any question, guys? Okay. Now, please also understand, and this will become clearer, is this p-value. The p-value of what? P-value of t statistics. Okay. If the p-value of the, so again, what is my null? The null is the beta is equal to 0. And if beta is equal to 0, it is telling me x is not impacting my y. Okay. On the other hand, if this is not equal to 0, it implies x is impacting y. Okay. So please note, and you can take this as rules of thumb. What is the rules of thumb? If the value of t statistics, if the value of t statistics is greater than 2.5, with surety we can claim that this x is influencing y. Again, what was the formula? Alpha plus beta x plus epsilon. Okay, epsilon is the error, this is my intercept, beta is this thing. Okay, so in this case, what we are saying is, we are saying that if the p-value, and if t is greater than 1, be rest assured the p-value of the t statistics, the p-value of the t statistics is going to be less than 0.01. Okay, and what it means, out of 100 times, maybe 99 times I will have beta equal to 0, and therefore I'm not including the beta. Okay, and 99 times beta will have an impact, only one time it will have no impact. So therefore we are rejecting or failing to accept the null. Okay, so this formula we are going to use for confidence interval. Okay, so keep that in mind. So basically, if I rewrite this formula, this formula is going to be beta 2 minus t alpha 2. This is the t value at 5% level times standard error of beta. As we do it, it will become more clearer. I will do it right now. So hang on. T alpha 2 times standard error of beta 2 plus beta 2. Okay, so this formula, and this formula is we are going to use. This is the F test on model component, basically trying to say that which one of the variables we should include as explanatory variables while we are trying to predict our any price. So basically, in today's class, what we are going to do is as follow, using the data. And why I took a little bit more time in order to explain the intuition, because now it will become very clear as to what we are doing and why we are doing. The first is I will try to explain the Anova table. Anova table is nothing but it contains this explain sum of square, residual sum of square, and total sum of square. Again, just to refresh our memory, if this is my y bar, this is my y hat, This is the actual Y. So this up to this is RSS. This is ESS. And the total is ESS is the explained sum of square. RSS is something you cannot explain in spite of estimating Y hat. So that is my error. This is my error. And if I add ESS with RSS, I get what is called the total sum of square. Okay. We are going to talk about the F test T statistics and try to see what are the use of F test T statistics. We are going to talk about the T statistics. We are going to talk about a check for the endogeneity. The easiest way to check for that is whether there is any relationship between X and errors. So the way you do it is you multiply X with errors and you take the summation. If the summation is coming to be 0, there is no endogeneity. The data is exogenous. Alternatively, you can also check for the covariance between Y hat with error. And finally, we are going to do the prediction of the forecast or the projection. Okay. So this is what is we are going to do right now. Any question, guys, before I start using the data? Intuitively, if you have any question, please feel free to ask. Okay, that's a good news. You don't have any question. So let me go back to our data set. Okay. Are you able to see the screen? Okay, after I showcase this, what I'm doing right now, I'm going to ask you is, I'm going to share another database with you. Please do it by yourself. Only then it will make sense. Okay. So here, what I have is, as I said, that I have my sales price and the square feet year bill lot size. The way I have collected the data is on the basis of stratified sample. And let's say that I'm trying to do the data analysis. And for those of you who were there in the previous class, I also said for the t value, if you want to change the t value, there is a function called goal seek. Okay. So that we are not going to use right now. I told you that I'm not going to spoon feed, but maybe some of you have. This was in the context of one tail and two tail test, and Dr. Arjun has already shared that data set with you if you were to. So under that was one of the questions, that at what level of significance will the t test statistics will be statistically significant. Okay. Okay, so let's try do this. So data analysis, and then I go to, yeah, you guys can see my Excel file, right? Yes, right?
Yes, sir.
Yes.
Yeah.
Yes.
Okay. So let's go for the data regression, and then you have this. What I said is you look into, you mark the label, okay, and you have to click on the label, because I want to understand where. And by the way, Excel by default is giving you 95, but if I want to keep it at 99, I can always do this. And now I have to give the output range, and let's say that I want my output range to be here. Okay, there are a few other additional thing I can do. Is typically what you do is you want to plot the residual. Because why? Because the residual is an important factor which I should see. Two things. First, the sum of the residual should be equal to 0. Second, to test for the endogeneity, I should multiply. I can multiply any one of the x and then try to see whether that there is any endogeneity. That residual, the summation of x multiplied by residual should also be 0. Okay. So let's try do this. If I do this, this is what I'm getting. Let's try to check one by one. Okay. So what you have here is, this is that ESS. So the first thing that you see here is, this is that ESS. This is what we are calling RSS. This is what we are calling TSS. Okay. I spent so much time in explaining you all of this. So this is what you are getting in terms of number. Now, this number, this is called mean square. Okay? This number you are getting, if I'm dividing SS, so if I'm dividing SS with the degree of freedom, okay? Degrees of freedom. If I'm dividing it with degrees of freedom, is what I get. You can check it yourself. So for instance, if I'm dividing this over this, I get, see, 1095, you get the same thing. Likewise, if I'm dividing 17, if I'm dividing, let's do this, and I'm dividing this over this, I get this number 38 something. So this minimum mean square, mean sum square is nothing but it is the sum of square adjusted for the degrees of freedom. And then F, by the way, these two are following a chi-square distribution. And if I take the ratio of these two, I get what I get is what you see over here as F test. Okay. So this is the value of F test. See, 28.71. You are also getting 28.71. Now, this F test statistics is highly significant. How I know that this is highly significant? I have to write this formula F test. And then X is F, this is 28.71, and your degree of freedom here is 4, and your degree of freedom in the here is this one, and you get the F test the same as what we are getting. So this is the P value of the F test. What is this? This is the P value of the F test, which is highly significant, highly significant, because this is 0, right? So this is E minus 12 means point, there are 12 such 0, okay? And then I have this 7, okay? So there are 12 such 0. So this is basically 0. So what it's telling me, if I have 100 as the sample size, out of 100 times, Y hat is a better predictor than Y bar. Okay, what is Y bar? Y bar is the average. So basically it's saying, and here you see, if you look into this data, this is my predicted value. Okay. So predicted, if someone asks you that what's the prediction? So that is my forecasted value. Okay, so this is my predicted value. And what the F test is saying that out of 100 times, in all the cases, my predicted value is doing a better job than Y bar. Now, when I say it's doing a better job, that means if I'm considering Y bar, I'm going to get less error. Okay, so that's what means by better job. Okay, clear, guys? Any question, please feel free to ask. Okay, no one is going to intuitively explain like the way we are doing right now. Okay, so here let's try to see about our other things. Okay, the other thing we said that if I'm adding the error terms, it should be, ideally it should come to 0. I don't know whether what we have said is correct or not. So let's try to see. Ideally it should be the case, otherwise we have done something wrong, because this is the conditional, this residual is we have derived on the basis of the conditional mean. Let's see. Ideally it should be 0. Bingo. You find that this is equal to 0, because this is basically point followed by 90 and then comes this. So this is 0. Okay. Now let's try to check for the endogeneity. Okay. Let's try to check for the endogeneity. So for doing that, you can choose any x. Okay? So let's try to choose one of the x. Let's say which one of the x is statistically significant? Square fit is highly statistically significant. I'm going to come into that in a moment from now, but before doing that, let's do this. Okay? So I'm converting the data. So here I'm checking for the endogeneity between using the variable square fit. Okay? So this is what I'm getting. So ideally, this should also be equal to 0. Otherwise, we have a problem of see, this is also 0. Okay. So this is also 0, basically saying our data is not suffering from endogeneity. Okay. So any question, anyone? So you can